Yeah, well, first, thank you very much for the introduction and the presentation, and inviting me to be here. I am always very glad to be here in India, and in Bengaluru is my third time here. Then I have written some notes for the course, and they are now in the web page of the course. And the interesting thing of the notes are mainly the bibliography at the end, so you have bibliography for everything that we will discuss. Then finally, the talk will be mainly about the essential minimum of height functions just on the projective line. And I have to start exactly where Fabian ended. So I will repeat the last two talks. So remember, what is a height? A height is a function that in some sense gives you an idea of how complicated an object is from the arithmetic point of view. For instance, if you're interested in geometry and you're interested in curves, then geometrically the degree is what tells you how complicated a curve is. So if it is very high degree, then the curve can move a lot. If it has degree 1, it's just a line. Then the arithmetic analog is what is called the height, that in truth is the arithmetic analog of the degree, and is telling you, for instance, how difficult it is to put the arithmetic object in a computer. As we have seen in the talk by Fabian, if the height, we can think that is more or less how many digits you have. No? Let's start with the height of a rational number. So R alpha is a rational number, P over Q, and we are assuming, for instance, that P is bigger than 0, not important, and the greatest common divisor of P and Q is 1, so they are coprime. Then the height of alpha will be equal to the log of the max of P and Q. Okay? So this was the definition of height that appeared in Fabian's talk, but I will call this the Wiles height, because the idea is that there are many functions that will satisfy the same property. For instance, variance. I can write h1 of alpha to be log of absolute value of P plus absolute value of Q. This is also a measure on how many digits I need to compare. Or I can define h2 of alpha to be just log 1 over 2 log of the absolute value of P to the square plus the absolute value of Q to the square. This will be the Fubini-Studi h2 or h Fubini-Studi of alpha. There are many possible variants of the height, and they satisfy more or less the same properties, because, for instance, if I compare the Wiles height and the one height, I have that HW is always smaller or equal than H1, because here I am taking just the log of the max, I am taking here the log of the sum. But of course, this is smaller or equal than HW plus log of 2. Hence, the difference is about the function. And so if I am looking at finiteness properties, there will be no difference between using one or the other. Okay, so the important point is that high functions, there are many high functions, and depending on the problem at hand, you may be interested in one high function or another, and they will have different properties, as we will see. Okay, now let's go to the next step. As we saw in Fabian's talk, one starts discussing what is the height of a rational number. Here it's very easy to understand that the height has to do with the size, but let's go to algebraic integers or algebraic numbers. So let's now take alpha, an element in Q. I will give the same definition of height. The Wiles height will be the same as Fabian, but I will give a different formula, maybe with less requisites. If I start with an algebraic number, I know that there exists a unique polynomial, P of alpha, that is in set of X, a polynomial with integral coefficients that satisfies the following properties. The first property is that, well, P alpha will be AD x to the d plus A0. Okay? Now, the first property is that P alpha applied to alpha has to be equal to 0. The second property is that I want P alpha to be irreducible over the rational numbers. So I don't want to add spurious factors. The third property, in some sense, is that I want it to be also irreducible over the integers. So I want that the greatest common divisor of all the coefficients is equal to 1, so the coefficients are coprime. So this is called primitive. And since I want to be only 1, I have to add a last condition for that AD, I want it to be strictly bigger than 0. Okay? With these conditions, this polynomial is unique, and this is called the minimal polynomial of alpha. Now I can look at the zeros of this polynomial. This is a finite set of the complex zeros inside C. This will be a finite set of betas. Exactly beta I equal to 1 up to D. They are exactly the elements. This set of zeros is also what one calls the Galois orbit of alpha. Okay? And these guys are the conjugates now from an algebraic point of view, there is no way to differentiate alpha or one of these beta i's. Because if I get, given, imagine that I take beta I, so this is inside C. So now, for every I, there exists an embedding, let's call it iota, from Q bar to the complex numbers, such that since my abstract object alpha was an abstract element in Q bar, is sent to beta I. So I can make an embedding of the closure of Q inside C that sends alpha to any of these conjugates. So all the conjugates in some sense are equivalent from an algebraic point of view. I cannot distinguish between them. And hence the height should be something that does not depend on alpha, but depends on the set of conjugates. Okay? So my definition, the Wiles height of alpha will be just, on the one hand, I need to compute the logarithm of the main term. So this main term, one can think of it as some kind of denominator of this algebraic number. And then the sum from I equal to 1 up to n of log of the absolute value of beta I, the size of the conjugates, and then I will divide by 1 over d. Okay? So we can think that the height will be more or less the size, log plus, where log plus of a number R is just the max between 0 and log of R. Okay. So we can think that the height tells me something about the size of the denominator and the average size of all possible conjugates. Okay. The log of the AD is the main term here. It's like the denominator. So you see that, for instance, if I start with a rational number, alpha is equal to P over Q, what is the minimal polynomial? The minimal polynomial is Q alpha minus P. And then the roots, now there is only one root, which is alpha, and then we can recover this formula. It's exactly this one, in the case D is equal to 1. Okay? And this is why I say that alpha, we can think of it as the denominator of the equation. Yes? Sorry. Thank you. It's good to see that people is awake. Okay? 1 over D, yes, because I want the average. So it's 1 over D, log of AD, and then, okay? Well, in some sense, this is a more elementary definition of the Wiles height. And this is what one can call a global definition, in the sense that it involves the denominator. But there is another formula that we have seen in Fabian's talk. So this is the global definition. But there is a local definition that involves an infinite, a priori infinite sum over all possible places. So the other local definition will be as follows. So I need to write M of Q. This is the set of places of rational numbers. Remember that the set of places consists of the symbol infinity and then the absolute value infinity of x is just the usual absolute value, and then the symbols p prime, and then the absolute value of xp is just also if x is equal to a over b times p to the d, where a and b are co-prime with p, then this will be just p to the minus d. Okay, so higher powers of p are smaller with respect to the p-adic absolute value. So this the set of places of Q is just the set of all possible non-trivial, non-equivalent absolute values, normalized in such a way that if I take the product of all the places, be inside M of Q of the absolute value of x, b, this is always equal to 1. Because you see, if you write down x, the expression in products of primes, on the usual absolute value, you will get the prime p at the power d. In the p-adic one, you will get p at the product minus d, and then the product of all of them is minus 1. Okay, with this definition, now the formula of now for every b, remember that you can start with rational numbers. Then you construct the completion that will be either the real numbers if b is the Archimedean absolute value, or the p-adic numbers if it is the p-adic absolute value. Then we can go to the algebraic closure of this guy here. And now it depends if I am in the Archimedean case, I finish because I already obtained the complex numbers. If I am in the p-adic world, I start completing. Now I go to the algebraic closure, and now it's not complete, so I can complete again. Go to QB bar hat completion, and this is the field that I will call CB. Okay, so this CB is a field that has the absolute value, extends the absolute value, either the p-adic one or the non-Archimedean one, and is complete with respect to this absolute value. Now this orbit, here I have defined the orbit of alpha inside C, but you can solve this polynomial in any of these fields. So you have the orbit of alpha in all of these fields, and then you can define the height by height of alpha. This will be just the sum 1 over d, and then the sum for all b inside the places of Q, and then the sum for all beta inside the orbits of alpha inside C of b of the absolute value of the log max of the p-adic absolute value. Okay? And this is more or less the same formula as Fabian was writing, because if you look at the sum for all places of Q, and now you look at all the conjugates of beta, this is more or less the same as looking at a Galois extension of Q that contains all the conjugates of beta, and then summing over the classes. Okay. Questions so far? So this is the definition of the height of a point. Now I can add, so here I have defined the height of an algebraic number. Now I can try to define the height of a point in the projective space. Okay. If I look at heights of points in the projective space, let's imagine that I have a point P, that is x0 dots xn. That is a point in Pn of Q bar. And I want to define the height here. Then what I can do is to find K, a number field, such that the point P belongs to Pn of this number field. So I know that since there is a finite number of coordinates, there will always be a finite extension of Q that contains all of the conjugates, and I can, for simplicity, assume that it is a Galois extension, Galois over Q, and then I can define the height of the point P will be equal to 1 over D, where now D is just the degree of the extension, and then I take the sum of, for all places of MQ, and then the sum for all sigma in the Galois group of K over Q of log of the max of iota B of sigma of xi. L max from I equal to 1 up to n, okay? So let me see here, iota B is just an embedding of Q bar inside CB. I choose a particular embedding, so I know how to send any algebraic point to CB. But the problem is that I have to be sure that things will not depend on this embedding. So what I do here is to sum over all possible the action of the Galois group of K over Q of sigma of this here. And then the fact that I am adding over all elements in the Galois group makes it irrelevant which is the embedding that I choose, because in some sense this effect is the same as changing all possible embeddings. And I take the log of the max for all of the coordinates, sorry, for I equal to 0 up to n. Okay. Observe that, for instance, if my point P was of the form 1x, now when I take the max of all the coordinates of 1 and x, this is exactly the same as log plus max of absolute value of 1 and absolute value of x. This will be log plus of absolute value of x. And here I need to add the b-adic absolute value here. So we see that we can extend the height. We have defined the height for numbers, for rational numbers, the height for algebraic numbers. Now we can define the heights for points in projective space. And in particular, if I restrict to P1 and embed Q bar inside P1 of Q bar, I get exactly the same height I had before. Okay. Now, I want to define heights for points in projective varieties. So let now X a variety defined over the rational numbers, for instance. And then I want to define a height from the algebraic points of X to the real numbers. How can I do that? Now, since I know how to define heights of points in projective spaces, what I can do is to choose an embedding X inside Pn for a very big n, phi. And now you can define the height with respect to this embedding phi of a point X just as the Wiles height of the point P of X. Okay. Once I know how to define heights of points in algebraic spaces, then I can define heights on arbitrary projective varieties. Now we can see example we see that now this gives a lot of choices because there are many ways to embed a variety inside Pn. And every embedding will give me a different possible height. For example, I can look at P1, and I can embed P1 inside P2, sending the point xy to the point x, then the point, what was the mission? Yeah, y minus x, and then the point x. Okay? And now I can define the height of the height with respect to this phi of a point of the point alpha 1. This will be 1 over d log of AD as before, plus, and now the sum for all beta inside the orbit of alpha. And instead of the function log plus that I had there, I just get log of the max between, let's maybe write it down here so I don't cross the line that I cannot cross, plus log of max between absolute value of beta, absolute value of 1 minus beta, and 1. These are the adic absolute value. And this is this max. So you see, starting with the Weyl height, just by choosing a different embedding into Pn, I now get a completely different height with different properties. Okay? Now, all the heights that I have defined, the Weyl height or any of these algebraic heights satisfies this North code property, which is disappeared already in the talk by Fabian, and is in some sense the important property of a height. So a good height satisfies that the set of all points inside X of Q bar, not just algebraic numbers, but points on any algebraic variety, such that the degree of the field of definition of the point K over Q is finite, is bounded by some A, and the height of X is bounded by some point B. This is smaller than infinity, so it's a finite number, the number of points here. And you see, this is the key point for many finiteness theorems. For instance, this was the trick used by Faltings in his proof of Mordell theorem. He defines a specific height. In this case, it's a case of modular height. It's a little bit more complicated than the height I have described because it might have singularities, but at some point he proves this North code property, and this is one of the main ingredients to prove that every curve of genus bigger or equal than 2 over a fixed number field is fixing this degree, is a finite number, just by proving that the height is bounded. Okay. But the important thing I want to convey is that we don't have a single height. We have many possible choices. And in every problem, the height we want to use can be different. For instance, if I am in a modular problem, I might be interested in a height that has something to do with the modular problem. Okay? Or, and this will appear possibly in the talk by Fabian. Or if I am in a dynamical system situation, I might like to use a height that is invariant under the action of the dynamical system. Now, when one has a height, the first question we can ask is, what is the spectrum of this height? So what are the possible values of the height? Okay. Now, typically we have an interesting value, which is the absolute minimum. So let H be a height. Then, of course, we have the first interesting invariant, that will be the absolute minimum. The absolute minimum will be just the infimum of the height of x for all points x inside x of u. But in many cases, it might happen that my variety has a subvariety, which is very special, and then the height of points in this subvariety can be very small. But if I look at a generic point, the height is much higher. So I want to see if truly this absolute minimum is attained just by a happy coincidence, or truly is a value that many points can achieve. And for this, one can define the successive minima. That are defined as follows. So E sub I will be the supremum for all y inside x of defined over Q, the codimension of y equal to I, and then the infimum of the height of x, but x now is a point that belongs to x minus y okay. So let's see a little bit what I am doing here. So I am, for instance, if I look at, So let's imagine that x is irreducible of dimension n. What will be the minima n plus 1? The minima n plus 1, well, how many subvarieties of codimension n plus 1 I have on x? None, because if my variety has dimension n, I cannot have things of codimension n. So this supremum is not here, I cannot subtract anything, so I have the infimum of all points in x. So I get the absolute minimum of my height function. But what happens if I look at E1 of my height function? Now, I have the right to subtract anything of codimension 1. Observe that any proper subvariety is of codimension 1, because I am assuming that x is reducible. So I am looking at the minimal possible value of the height after subtracting anything. Okay? I can subtract any set. Of course, what I subtract has to be algebraic of codimension 1. So whenever I subtract some y, there are a lot of things here. So what I get is what we can call the essential minimum of h. That means that is the minimal possible value of the height for generic points. Okay, so what happens is that I have a subvariety that concentrates a lot of small points. But when I take out this subvariety, then the height is much higher. Okay, you see that this minimum, in some sense, is telling you what is the minimal possible value of the height of a generic point. Of course, there will be points, special points, that will have a smaller height, but the essential minimum will give you the and then there are a plethora of minima depending on how much I am allowed to subtract. So for instance, the En, I will only be able to subtract a finite set of points. And this will be the difference. So I have a plethora of minima. And then it is important to know these values will tell me a little bit about what is the distribution of this height function. Okay? Now, there is an inequality of sum that tells me the following. So I have talked today about heights of points. If you remember the talk by Fabian, he said, okay, we have the heights of rational numbers, height of algebraic numbers, height of point of projective spaces, heights of points on algebraic varieties, but then heights of algebraic varieties. So you can now generalize this and define the height of a variety. And you can define the height of a modular space, and blah, blah, blah. So it can generalize. So I have the right to talk about the height of a variety x. And it turns out that the height of x is always if I normalize correctly, so there are several schools and one normalized dividing by the dimension and d+1, but let's take the normalized one. This is always smaller or equal than E1 of X, the essential minimum of X. And this is always bigger or equal than 1 over d+1 and the sum for I equal to 1 up to, n. We were saying the dimension is n. Okay. n+1 of sum from I equal to 1 up to n of E, n+1 of E I. Okay? So that the average of the minima is always smaller than the height of the variety, and the height of the variety is smaller than the E1, that is the bigger possible. For instance, if we are in the Weyl height of the projective space, it turns out that the height of the projective space with respect to the Weyl height is 0, the essential minimum is 0, the absolute minimum is 0, and every guy is 0, and this collapses. But imagine that I can find, so this implies that if there exists a point P such that the height of P is smaller or equal than the height of X, then automatically E, the absolute minimum of X or H, is strictly smaller than the essential minimum of H. So the moment that you can find a special point whose height is smaller than the height of the variety, it's smaller, then automatically I cannot have this sandwich to be an equality everywhere because this term will be smaller than this term here, and then automatically I will get that the absolute minimum has to be strictly smaller than the essential minimum. And for instance, at some point when Sang make this very abstract and not very concrete theorem, then Sagier worked a little bit to find the easiest possible example of a height where this happens. And it turns out that his solution was exactly this example here. A little bit different, but morally just this example where you put P1 inside P2 and consider the Weyl height in P2, but restricted to P1, is an example where we get that the essential minimum and the absolute minimum are completely different. Okay. Questions so far? Okay. Since I want to convince you that the essential minimum is important, let me explain to you a theorem where this essential minimum appears. And this is the so-called Bogomolov conjecture. Okay. So remember the Mordel's conjecture. This tells me that if I have C, a curve defined, for instance, over a number field, and I know that the genus of C is bigger or equal than 2, then the number of points in C defined over K, this is always finite number. Okay? Now, this is a very general topic in arithmetic that is telling you that, okay, curves I have the projective line, genus 0, the elliptic curve, genus 1, and then general type, which is all the rest, genus bigger or equal than 2. And then on special curves, P1 or elliptic curve, I can find many special points. But if my variety general is of genus bigger or equal than 2, then the number of special points has to be finite. Okay? Here, a special point means that all the coordinates are in the field K. This is a very special property, because in general, if I take an algebraic point, it will have coordinates in a very big field. The property of being special is to have coordinates in the field K. Now I can look at other instances of this principle. So for instance, I can look now at the Jacobian of the curve C. So this is an abelian variety. I fix a point P0 inside my curve C, and this automatically gives me an embedding of the curve over the Jacobian. So I can choose this point rational over some finite field. Now, on the Jacobian of C, I can look at all possible algebraic points. Here there are many points, but I can look now at special points. I can look at the points that are torsion. Okay? If I look at the points that are torsion, now I can ask, okay, who is C of Q bar? So all possible algebraic points, but I intersect with the points in the Jacobian that are torsion. So this is another kind of special points. So are points that when I embed in the Jacobian gives me something which is torsion. It's a very special property. Then the Manning-Mumford conjecture tells me that this guy, if the genus of C is bigger than 2, then I automatically get that this number of points is finite. Exactly the same kind of results. So if the genus is bigger than 2, if I have a curve of general type, then the number of special points is finite. Okay? This theorem was proved by Renaud, but then Bogomolov, at some point he says, okay, in the same way that we have defined the Duval height in projective spaces, and as Fabian told us, if I look at algebraic points, having height equal to 0 is the same as being a root of U1. And observe that being a root of 1 is that very much like being torsion, because it means that at some power it will be equal to 1. Now, if I am in an abelian variety, there is also a canonical height, the Nérontat height. So in J of C, there is a canonical height. H hat. And this canonical height satisfies the property that H hat of a point X is equal to 0 if and only if X is torsion. So I can detect if a point is a torsion point just by computing the height function on this special, very nice property. And then Bogomolov, so this theorem is telling me, okay, the points in the curve of height 0 is finite. The Bogomolov conjecture that was proven by Espirot, or by Ulmo in the case of curves, and by Zhang in the case of subvarieties of abelian variety, look, what it's telling me is that there exists an epsilon bigger than 0, such that the number of points inside my curve C Q bar with height, canonical height of X smaller than epsilon, this is finite. So not only the points with height 0 is finite, but there is a gap, so that truly I cannot find points with a small height. Okay, but now if you look at what is telling the Bogomolov conjecture in a curve I only have two minima: the absolute minimum, that may be 0 because maybe by chance I have a point that is torsion, and the essential minimum, which is the generic one, and which this theorem is telling me, so this is equivalent, as that the essential minimum of H hat restricted to C is bigger than 0. So the Bogomolov conjecture is just a statement about the essential minimum on a curve of a particular height. So we see that in some sense knowing what is the essential minimum is an important result. And we'll see later that this theorem was proven by Ulmo and Zhang, depending on the situation. And the key ingredient is an equidistribution result by Espirot, Ulmo, and Zhang. And we will discuss in another talk about the equidistribution results. And you will see that if we want to understand the equidistribution results, it's very important to know what is the essential minimum. Okay. Now, the essential minimum is a very well-defined real number. And everybody knows real numbers. I mean, real numbers are easy. It's the line. But if you start thinking a little bit, real numbers are terrible. I mean, if I give you a real number at random, you have no clue what to do with it. I mean, no idea what you can do with a real number. The point is that the numbers that we use normally, they are not just arbitrary real numbers, are numbers that comes from a method to construct them. And then you can do things. For instance, there is the theory of what is a computable number? A computable number is a number that you can produce an algorithm that in finite time, maybe more than the age of the universe, but in a finite time, you can approximate this number as much as you want with a algorithm, a finite algorithm, okay? This computable number, in some sense, is the minimal set that you can work with. If your number is not computable, you cannot say anything about it. Well, the set of computable numbers is countable, while the set of real numbers is huge. So if I give you at random a real number, it will not be computable. Of course, nobody will be able to give you a non-computable real number, but in principle, if you define a real number, it's not clear whether this number will be computable or not. Okay? You need to produce at least a theoretical algorithm to compute it. So one question we must ask is, okay, I have this very nice invariant, the essential minimum. This essential minimum appears in many theorems, but is it a computable number? So it's truly a number that I can have a grasp on it and have some idea what to do with it. Now, what I want to do is to go to the easiest possible situation where this problem can be stated. So, and let's try to study this problem in the simplest possible situation. Of course, now there is people enlarging the result to many more general situations, but at least let's discuss the simplest possible case. So I will work in, so I will work just in P1 in the projective line. And then I will give myself a function, G, from the complex numbers to the real numbers. I want this function G to be invariant under complex conjugation. Okay. And so this means that G offset bar is equal to G offset. And I want that this function, when the absolute value of set goes to infinity, when I approach the point at infinity, I want this to be like the log of the absolute value of set. And then I allow myself a small error term. And the error term is, since I want to have log set, the biggest error term I can imagine that does not disturb this is just a small o of log of absolute value of set. Okay, so I give myself just a function on C that is continuous, of course, because if it is not continuous on C, then I will not be able to do many things. So it's a function on C, which is continuous on C, and that has this asymptotic when I approach the point at infinity. And then I define the height of a point, the height G of the point alpha 1. So the height of an algebraic point in P1 will be just equal to now 1 over D log of AD, and then the sum for all beta inside the orbit of alpha of G of beta. Here I am using all the notation as before. So I have my polynomial P alpha that will be AD x to the D plus A0, okay? And then the O of alpha is the same as the zeros of my polynomial P alpha, okay? So observe that this definition is more or less the same we obtain for the byte height. The only difference is that instead of writing here the function log plus of absolute value of beta, I am using just a general function G that satisfies these properties here. It's invariant under complex conjugation, satisfies this asymptotic when set goes to infinity, and is continuous on C. Okay. Now we can think that this is a very restrictive question, But let me give you several examples. So the examples, first one is I can consider the function g of z to be just log plus of absolute value of z. In this case, the height I obtain is just the Bell height that we have defined before. Or I can define the function g of z to be just 1/2 log of 1 plus absolute value of z to the square. And then I obtain the Fubini's 2D. The Fubini's 2D height. These are the easy examples. Then the third example is g of z will be just 1/2 of log plus of absolute value of z plus log plus of absolute value of 1 minus z. Okay. I have to divide here by 2 because the asymptotic of this one when z goes to infinity is log of z. This is also log of absolute value of z, and then I have to divide by 2 by. Okay, this function has was the one introduced by Zagier. So Zagier introduced it in his original paper to study this problem, this is the minimum. One was this height, the projective one, but the other one was this other one. So this is what is called the Zagier height. In this case, I obtain h of g is h of Zagier. And this height has been studied by many authors. For instance, Flaman, Doce, Zagier, and so on. And there is a literature. Even I think this height appears, the essential minimum of this height appears in now a new list of interesting constants that are not known how to compute. So the essential minimum of this one appears in this list. Then the fourth example is just g of z to be 1/2, and now is the log of the max between absolute value of z, and absolute value of 1 minus z. And this was also introduced by Zagier, and is just a symmetric version of this one. Now observe that in this case, I am taking z and 1 minus z. In this fashion, here I am doing something similar. So the difference is that here I am embedding P1 inside P1 cross P1, and here I am embedding P1 inside P2. Okay. But things do not end here. So example number 5, I can take the function g of z to be, yes? Because I was just copying the part on top and I don't need it. Thank you. Yes. Good. Yeah, I don't need it. Okay. The next one will be log of 1 plus absolute value of z plus 1 minus z. So this is similar to this one, but slightly different. And this, as we will see later, this will appear studying the minimal vector of the lattice associated to the Grassmannian 2-4. So we'll see that we will be able to solve a problem in higher dimension in the Grassmannian 2-4, just looking at essential minimum in dimension 1. So this is related with the Grassmannian 2-4. Later, in the last talk, we will see something like this. Then there are other examples, 6, which is g of z is equal to log. Now, you see that one can make a lot of different. This is 2 times z minus 1 plus 2 square root of z squared minus z. This is an absolute value, and then possibly minus 2 times. Okay. So this strange function, this also has a meaning, and is related with what is called the integral Chebyshev constant on the interval 0, 1. So the integral Chebyshev constant of the interval 0, 1 is exactly the essential minimum of this particular height function. Okay. Now, all of these functions satisfies that, so examples 1 up to 6 satisfy that G of set, when set goes to infinity, is like log of absolute value of set plus continuous. So it's a function that extends continuously to infinity. Why I have taken this singularity? Because of the next example. So let me introduce you the example number 7 that also falls in this category. Okay. So I look at the Y1, the modular curve of level 1 that appears already, Yn appears in the told by Fabian Pasuki. Here the only problem is that Y1 is not a true curve, but it's an orbifold. But if I forget the orbifold structure, it is P1, or maybe X1 will be P1. Okay. Then inside this here, I can look, I have the J invariant that when I apply the J invariant of E, it's an element in P1. And then I can define the height of the value G of E as what is called the Faltings height of the elliptic curve E. So Faltings define a height, a modular height, to every curve. And I can say, okay, since my points in P1 through the modular curve parameterize elliptic curves, I can define a new height in P1, which is saying, okay, the height of a point is just the corresponding height of the elliptic curve. Okay. Now I can give a precise definition of this. So I can define f of tau will be the modular form given by, not the modular form, but f of tau will be the log of 4 pi, the imaginary part of tau to the 6th power, and then the absolute value of delta of tau, where now delta of tau is the one that is a modular form. So delta of tau is just u times the product for n equal to 1 up to infinity of 1 minus u to the n to the power 24. And this where q now is equal to e to 2 pi I tau. This formula is for the people that like Ramanujan and modular forms. So this is the what is called the modular discriminant. This is the cast modular form of weight 12. Okay. Now, this modular form of weight 12, delta, of course, it is not an invariant function. So when I make the SL2 set act on the upper half plane, this will change. But adding these terms here makes me an invariant function. So this function is invariant. So this is a function that goes from the upper half plane to the real numbers, and is invariant under SL2 set. Since it is invariant under SL2 set, it defines a function, let's call it GF of G of Faltings from Y1, which is just the upper half plane divided by SL2 set, and that I can identify with C if I forget the orbifold structure. Okay, then this Faltings height is exactly H of J of E is just the same as the HGF of J. Okay, so this concrete modular form gives me a concrete function whose associated height is exactly the Faltings height of the modular curve. Now, the problem is that this function satisfies that when so this GF of set, when absolute value of set goes to infinity, this is like log of absolute value of set plus an error term, and the error term is of the shape log of it's right, minus 6 log of absolute value of set. So it has an not continuous error term. Observe that when z goes to infinity, log of z goes to infinity, log of infinity is infinity. So I get something which is not even bounded. Okay? But is a small o of log of z because it's two logs. Okay? And the good point here is that even if this height, the difference of this height with respect to the bell height is not bounded, still I have not got property. So this was one of the observations by Faltings in his proof of model theorem, that even if the modular height, the difference with the bell height is not bounded, still satisfies not-God property and gives you finiteness results. Okay. So we see that just this simple problem that I fix a function on C and try to compute what is the essential minimum has already 7 different interesting incarnations. And let me just finish with a small interpretation. So I presented the problem to make things, I have erased this. Yeah. To make things very concrete. So let me state again the problem. So I have G that goes from C to the real numbers. G of z equal to G of z bar, continuous. And G of z equal to, or asymptotic to log of absolute value of z plus a small o of log of absolute value of z. Okay, and then the height with respect to G is just 1 over d of the point alpha 1 is 1 over d log of AD plus the sum from I equal to 1 or beta inside the orbit of alpha of G of beta. Okay? So this is a very concrete definition of the height, and then we are asking what is the essential minimum of this height. But in fact, the right way to think of this is that, in fact, what I have is P1. On P1, I have the line bundle of 1. In this line bundle, I have the section Y. It's a section on H0 on P1 of O of 1, which is the section that satisfies that the divisor of the section Y is just the point at infinity, because it's the point where this guy will be 0, and so it's alpha divided by 0. Then I have a norm, a metric on O of 1, which is maybe singular at the point infinity. So it's continuous on C, but it might have singularities at the point infinity or not. So the important thing is that I have a metric on O of 1, and then my function G is just the logarithm of the norm of the section Y with minus sign here. And then, in some sense, there is a theory which is called Arakelov theory that defines heights of points, heights of varieties, and so on. And the basic ingredients are exactly line bundles with Hermitian metrics. Okay. The point is that since I want to keep things as simple as possible, I just give you the final result. So the height is defined just in terms of a function. But you have to think that, in fact, what I have is a variety, P1, a line bundle with a metric, and then the height associated to this line bundle and this metric. And this will allow us to generalize these results to arbitrary varieties. But for the moment, I want to present the results just for P1 to be a very concrete theorem that, in some sense, look at that is an interesting theorem because it is mixing, in some sense, analysis. I have a general function on C and arithmetic because I am looking at the essential minimum of something defined only on algebraic points. So I am trying to look what is the minimal value of the function on average on algebraic points. Okay? This is the problem that I want to say. So now the problem, determine the essential minimum of the height of a function G. So what can we say about this essential minimum? What methods are there to compute it or to approximate it as much as possible? And I think my time is over. So thank you very much for your attention.